Okay, so our goal is to come up with an expression, right? To actually derive a function, and we'll call that function t of n, a function of the running time of an algorithm with respect to the size of the input of that algorithm. So what do we need to know to actually write down this expression? Well, first, one thing we might think about doing is we might think about coming up with a list of all the different operations that this algorithm uses. So suppose we've done that. Suppose we've come up with our list and it has k operations in it. Right? So here's our list of all the operations, and so then we go and we look at each operation, and on our system we figure out how long does each of these operations take to run in say nanoseconds, right? So ti now is going to be the amount of time it takes operation I to run on our system in nanoseconds. And so we've got this list of operations, we've got this list of times. Now for each of the operations, we need to go and figure out how many times that particular operation runs as a function of the input size. So let me write c sub I of n to denote the execution count, right? So c now is a count. It's not a time. So this is the execution count of operation I. So I'll call this execution count of operation I. And now this is where our n comes in, right? So now this is with respect to input size. With respect to input size. So if I've got this stuff, if I have all of these things, then in principle, I can write down a complete expression for t of n. So what's t of n? Well, t of n is just going to equal t0 times c0 of n. c0 of n, right? So this is the total amount of time the algorithm spends executing operation 0, right? If you did a profiling and you looked at this particular operation, this is what we'd have. So it's t0 times c0 plus t1 c1 of n plus ... all the way up to t k minus 1 c k minus 1 of n. And I can rewrite this using some more compact notation in the following way. I can say this is from the sum from I beginning at 0 up to k minus 1 of ti ci of n. Right? And there's our expression. Okay, there's the whole thing. So if I circle this piece right here, that captures it. Okay. So what does this actually look like? So let's actually do a quick example, and I won't spend too much time digging into the details of this. I'll leave that to you. But let's do a quick example and just think a little bit about how long this might take for a typical algorithm. So we're going to take a particular algorithmic problem, a really, really simple one. All right, not going to add any complications here. And we're going to ask these questions in a detailed way about this particular problem. Okay, so this is the simplest search problem that there exists. This is a linear search. All right, so let's write an algorithm for linear search. All right, what is linear search problem? Well, we're given an array, A. And this thing, I'm going to represent this thing like this, 0 ... up to n minus 1. So this array has n elements in it. All right, so this will be my notation for array in my lecture notes. So this thing has n elements in it. And we're also given a search key. So we're given a number k. And k. So this is a number. What's our output? Our output is going to be the index in this array where k appears, right? So we're supposed to look through this array, find the search key, find k, and then return the index. And then if we don't find the search key, if the search key does not exist in the array, we return -1. So our output is index in A where k k appears, or -1 if it fails. Right? And so I could say or -1 if k is not in A. Right? That's a valid way of writing this. Okay, so here's one implementation of this, and it's not a particularly nice one, but it'll serve our purposes here. And in particular, I've designed this one so that every single operation, every single thing a computer is doing appears on its own line, so that we can easily take care of them. All right, so I'm going to call this thing. I'm going to call this SEQ SRCH, and this takes in an array, 0 and -1, and a search key. Okay. So first, I'll initialize a counter. So I'm gonna write my pseudocode in a very Python-flavored form. It's not exactly Python, but I think a lot in Python. I use a lot of Python for my prototyping stuff. So and it's nice clean code. So I'm going to use it for my pseudocode. So I'll initialize a counter. Initialize that at 0. So this is the first index. Then I'll start a while loop, and I'll say while I is less than n, and now I'm going to write this second thing on another line so that I have it separated. The search key is not at index I, so it's not equal to k. Then do the following. Then increment I. Okay, so this is inside the loop. Then the loop is done. So after this loop finishes, what I say is if I is less than n, which can only happen if this element was found, if k was found somewhere in the array, right? Because that's the only way this loop can break, other than I being equal to n, is if the element is found. So if the element is found, then what do? Well, I return the index. I return the place where this loop stopped. So return I. Otherwise, I'll return -1. Okay, and I'll often abbreviate return with ret. Okay, so now what I can do is I can think about how many times each of these lines of code is going to be executed as a function of the input size. Right, so let me number these. So I'll start at 0 here, and this is line 0, line 1, line 2, line 3, line 4, line 5, and line 6. All right, now you can refer to the notes in the class notebook for this particular figure, and so I'm going to scroll up and trust that you've got access to this through some of the means. Otherwise, you could run the video back, screenshot it, and take a look. Okay, so here's the question. How many times does each of these operations execute as a function of n? All right, so in other words, in terms of our mathematical language that we've established, what is ci of n, right? What is the execution count for each operation, each line of code, as a function of n? So this is for each I. Operation I. Okay, so I have a listing of this, and there's actually 3 different answers that I have put together in my table. And so let me write 0, 1, 2, 3, 4, 5, 6. And then let me write 3 different kinds of inputs where we'll evaluate this. So the first kind of input is k equals a of 0. Right? What does that mean? That means that the search key is found on the very first index of the array. It's found at the head of the array. If the search key is found at the head of the array, then the algorithm terminates very quickly because it doesn't have to search the entire array. So it turns out that we have 1, 1, 1, 0, 1, 1, 0. 1, 1, 0. right? So then this is the in some sense the best case Ci of n for each of these operations. So I'm going to call this Ci of n best up there. Okay. Now let me do two other conditions. So one of them is that the search key is not found anywhere in the array. So if k is not in A, right? That's not in A. How long does this thing run? Well, we initialize our counter just once, but then we do this many index comparisons. We do this many key comparisons. We do this many of whatever 2 is. 2 is a key. 3. So 3. Yeah. So 3 is we increment the counter. So we increment the counter n times. 4 still only happens once. 5 doesn't happen, and 6 happens once. Okay, and then there's one other case that we could think about looking at. It's not going to actually matter too much in our analysis, but we might as well work it out. And this is if k is the last element in the array. So k is a n minus 1. So in this case, we essentially just get one less iterate or operation count for each of these, for several of these. So this is still 1. This is n minus 1. This is n minus 1. And then we have 1, 1, 0, because a different return statement gets called. Okay. So here it is. So now we know the best thing that could happen for this algorithm as a function of n, right? All of those 1s, those are just functions of n. They're constant functions of n at 1, but they're functions of n. And then we also have an expression here for the worst case C of n. So this is Ci of n w for the worst case thing that could happen. And so now that the only challenge that remains is to combine these things all together into a full expression for the runtime of the algorithm.